Okay, now we are next looking at some exercises that involve quadratic inequalities. We have to solve inequalities which have the term x square. Unlike the inequalities we have so far got, which had only x, they can be called linear inequalities. But here we have quadratic inequality. So just like before, we have to express the solution sets as intervals or unions of intervals, and we have to graph the solutions. But we can turn such inequalities into an inequality that we have already seen, into a type of inequality we have already seen using this identity. So that's what we are going to do here for this one. So the 35th one is x squared less than 2. So we have to find all real numbers x that satisfy this inequality. Now here we are going to start like this. X squared is less than 2. This implies we will take square root on both sides, non-negative square root on both sides. The question is this justified? That is a legitimate question, and that question can be answered like this. If you try to graph this equation, you have to first of all make sure what are the values of x that can be taken as input. We can only take non-negative real numbers as values of x. Why? That is because what does this equation tell us? This equation tells us that y is a non-negative real number whose square is equal to x. That's the meaning of this equation. That means y is a non-negative real number such that y square is equal to x. That sort of number y is. Now we already know from properties of real numbers that the square of any real number it can never be negative. It is either positive or 0. So y square is greater than or equal to 0. So that means x must be greater than or equal to 0. And that's why we can only take such values of x. Okay. Now if one draws the graph by, say, putting some values of x and then calculating square root of x and plotting points, joining them, usual graph drawing, then roughly the curve will look like this. Okay, since we can take only non-negative values of x, so the curve, no part of the curve lies on to the left of the y-axis, because here we have negative values of x. This is the origin, this is the positive direction of the x-axis, this is the positive direction of the y-axis, and the graph goes like this, and it keeps on increasing. The y value keeps on increasing and it never ends. Okay, the higher the value of x, the higher we have the value of y is also more. Okay, now being able to take square root on both sides is equivalent to this. You see, we have x square here somewhere. We know that x square itself is a square, so it's a non-negative real number. It cannot be negative. So it either lies at the origin or to the right of the origin, and 2 is given to be greater than x square, so 2 lies there somewhere. Now if you join these lines, or if you draw perpendiculars through these points, then the perpendiculars will meet the graph at some points. That point will determine the values of the square roots. Why? Because you see, this point is, you say you take any arbitrary point x here, then if you draw a perpendicular line or a line parallel to the y-axis, then according to how you draw graph, the coordinates of this point are x comma square root of x. So the y value this much, this is the square root of x. So since the graph is increasing, you can see that as the input increases, the output also increases in size, and that's why here you see x square is less than 2 and square root of 2 is also greater than square root of x square. So that's why we have this inequality, and the converse is also true. If this is true, then this is true. Okay, so we will need the converse when we write the inverse implications. Okay, so this is why we have this. Okay, now we can use this identity to write in place of this our usual absolute value of x. So this quadratic inequality has been turned into an ordinary linear inequality, if you want to call it so, because it has only x, but which involves absolute value. Now this is a type of inequality we already know how to solve, and we already know that this implies that these inequalities are true. Now if one wants to go back, we have to be able to go back to find or to say that this is the set of all values of x for which the given quadratic inequality is true, and we can do that. We can go back. This definitely implies this. This implies this. Here we are simply again writing in place of absolute value of x, we are writing square root of x square. Now this also implies this, and that is also clear from the graph. If you take 2 points on the y-axis instead of on the x-axis, they are also maintaining some inequality between them. You draw 2 horizontal lines passing through those points. They will meet the graph at some points. The point which is lower than the one which is on top of it or which is above it, that will meet the graph at a lower level. So looking at the graph, you can clearly see that then from those 2 points where the horizontal lines meet the graph, if you draw perpendiculars, then the perpendicular, the feet of the perpendicular will satisfy an inequality like this. So the feet are the inputs for which the chosen points are the outputs for this function. So that's why you can take the inverse implication also, that is also true. So this inequality also implies this inequality, or in other words, what you ordinarily call or what you ordinarily say you are doing is that when you come across such inequality, you take squares on both sides. You can do that, okay, and that gives us this. So hence the solution set, let me write there, is the open interval -2, 2. Graph of this we already know how to draw. The graph will look like this. So this is -2, this is 2. The graph will be the line segment that lies in between -2 and 2, without ever taking these two values, because we cannot take either 2 or -2, because their squares, both of them are equal to 4, which is not less than 2, which is greater than 2. Okay. Oh, sorry, what the hell have I done? Here I forgot to take square root. sorry about that, square root. So sorry about this silly mistake. So we cannot take either square root of 2 or minus square root of 2. Okay, so this is the solution set, which is a single open interval. I just want to, although this solution is over, I just want to show one more way of doing it, although that is somewhat not this neat. That is somewhat long-winded. Long-winded means it is a little long. It does not involve bringing absolute value. It goes something like this. X square is less than 2. This will imply x square minus 2 is less than 0. Now using elementary algebra, you can write this as x plus square root of 2 times x minus square root of 2, because that will give us x square minus square of square root of 2, which is 2. Now you look at this inequality. It's a product of two real numbers that is less than 0. That means it's a product that is negative. So the possibilities are this. Either this is positive and this is negative, or the first one is negative and the second one is positive. So we look at both the possibilities. Say we first look at this possibility, the second one. Say this is negative and this is positive. Note that none of them can be 0, because if any one of them is 0, at least one of them is 0, then the left hand side is 0, and 0 is not less than 0, 0 is equal to 0. So that's why we cannot take equal to 0, that possibility is not there. Now this is equivalent to the first one, this, and the second one is equivalent to this. Can this happen? Can x be simultaneously less than minus square root of 2 and greater than plus square root of 2? Definitely it cannot happen, because here x is negative and here x is positive. So this is not possible. So that means this is not possible. What about the other possibility? X plus square root of 2 is greater than 0 and x minus square root of 2 is less than 0. From the first one we get this, and from the second one we get this. So yes, here these inequalities can simultaneously be true, and they give us this thing. Which is the same as the one we have got, the inequalities we have got. So clearly you can see that here it is somewhat longer than this one. So that's why it's better to bring absolute value. However, this is also a technique that can be used to solve quadratic inequalities. Okay, now so that's the 35th one. So like this we can now okay, let me write the 36th one here itself. Four less than or equal to x square. we have 4 less than or equal to x square. We can directly write double implication. Okay, we take non-negative square root on both sides, which we know we can do. This is equivalent to, this is 2. This is not minus 2, keep that in mind. This is, by definition, this symbol means non-negative square root. And the last inequality is equivalent to this. X is greater than or equal to 2 or x is less than or equal to minus 2. For an explanation of how we wrote that these inequalities, the final ones, you go back to previous exercises and there you will see how we get these inequalities from this, and in fact they are equivalent. If this is true, then these two are true, and conversely. Hence, the solution set is, in this case, it's a union of two intervals, minus infinity comma minus 2. Minus 2 is there, just like that 2 is also there, union 2 comma plus infinity. So that is the solution set, and accordingly you can graph the solution set also. Then this is 36. (37). 4 is less than x square is less than 9. Okay. If you find it difficult to conclude at once after this, then you can split them into two inequalities and work on each one of them separately. From the first one we will get this, or in fact we can write like that. That will be much easier to understand. This and this, if and only if the first inequality gives us these things: x is greater than 2 or x is less than minus 2, and this one gives just this, which can be written together. Okay, so the solution set is a combination of the intervals that arise from these inequalities. Either x is greater than 2 and these things. Okay, that means either x is greater than 2 and less than 3. If it is greater than 2, then it's automatically greater than minus 3. So that need not be written. So that means greater than 2 and less than 3, or x is less than minus 2 and greater than minus 3. That means union this. If you find it confusing how I wrote these intervals, you can always take the help of, in fact you can draw the graph itself. We have say 0 here, this is the positive direction of the real line. So this is 2, this is 3, this is minus 2, this is minus 3. X is greater than 2, say, and at the same time x lies in this interval. X lies in this interval means x will lie to the right of minus 3 and to the left of 3. Simultaneously, x has to be greater than 2, so x has to lie to the right of 2. So that means the first interval is this one. X already lies in this region, but now x also has to lie to the right of 2, or being in this region, x additionally has to lie to the left of minus 2. So that's why this is the other interval, and that gives you the graph also. This time the graph is broken, it's not a continuous line, it's the union of these two line segments where neither of them has any of its endpoints, no boundary point is there. Okay, so this is the solution set. So next 38. We have if and only if one by 9 square root of x square. When you are taking square root on both sides of an inequality, you have to always make sure that the numbers of which you are taking square roots are all non-negative. If you have something like this, then this does not imply in fact this second statement is meaningless because of a particular reason. Right now the thing we need to know is that when we are taking square root, the number of which we are taking square root, it has to be non-negative. Okay, it has to either be 0 or positive. Okay, so you can try to see like this. Here you have 1 by 2, here somewhere you have 1 by 3, 1 over 3 is less than 1 over 2, 0. Okay, so the second inequality tells us that x has to lie to the right of minus 1 by 2 and to the left of 1 by 2. That means this. And the first inequality tells us that x is either greater than 1 by 3 or less than minus 1 by 3. So that means here, just like the previous exercise, this is the these are the two intervals where x can lie. So that means yeah, we can write like this. Or this. So the solution set is this open interval minus 1 by 2 comma minus 1 by 3 union 1 by 3 comma 1 by 2. Here also, because of strict inequalities, the boundary points are not part of the solution set. I can write exercise 13(9) here itself. X minus 1 whole square is less than 4. Same technique here. Instead of x square, we have x minus 1 whole square. After all, that is also a variable, x minus 1. You can think of it as y. Minus 2 is less than x minus 1, which is less than 2, and this is equivalent to, you add 1 throughout, get minus 1 is less than x, x is less than 3. So the solution set here is the open interval minus 1 comma 3. Then exercise 40. X plus 3 whole square is less than 2. Minus square root of 2 is less than x plus 3 is less than square root of 2, and only if subtract 3 from all the terms, that gives us minus 3 minus square root of 2 is less than x, and this is less than minus 3 plus square root of 2. So here the solution set is, let me write here, minus 3 minus square root of 2 comma minus 3 plus square root of 2. Then 41. This is less than 0. Okay, so although we have a square here, but we have x also. What to do in this case? You can get rid of this x by completing the square. That's how we usually say when we have an expression that has both x square and x. We apply the square formula, a minus b whole square or a plus b whole square. So we can solve this one like this. X square minus x less than 0. See, one wrong step would be to add x on both sides, thus getting x squared less than x and then taking square root. Always keep in mind that if you write the given inequality like this, that there is no problem. Till this it's okay. But then you cannot take square root on both sides. Why? Because you would not know, or would you know? Oh yes, no, we can take square root. The reason for that is this. Now we can take square root. I was thinking of something else. Although we don't know what x is, but x square is always greater than or equal to 0. So because x is greater than x square, x is positive. So x square is non-negative, x is positive. So yes, we can take square root. But then what do we get? After this we have absolute value of x. But here we have got square root of x. What shall we do with this? Once you get to this stage, after this you don't know what to do. So that's why this is not the path to follow. Instead, we will do this. X square minus, we try to make it 2 times something. So since we take 2 extra, we have to take x divided by 2. This is less than 0. And this we can write like this. X square minus 2 times x times 1 by 2. Now, if we have plus 1 by 2 whole square, then that will give us a complete square, x minus 1 by 2 whole square. We don't have that, so we just simply write the extra term like this. So we have to add that same term on the other side also. So this gives us what? See, x square minus 2 times x times 1 by 2 plus 1 by 2 whole square. So this gives us x minus 1 by 2 whole square. This is less than 1 by 2 whole square. Now you can take square root. Square root of this will be 1 by 2. add 1 by 2 to all the terms. That gives us 0 is less than x and x is less than 1 by 2 plus 1 by 2 is 1. So the solution set in this case is the open interval 0, 1. And finally, exercise 42. X square minus x minus 2. This is greater than or equal to 0. Okay, so the first two terms are just like the previous one. This minus 2 is greater than or equal to 0. So we can at once write many things. 2 times x times 1 by 2 plus 1 by 2 whole square means 1 by 4 minus 2 minus 1 by 4. This is non-negative. If and only if this part gives us x minus 1 by 2 whole square, and this part gives us minus 4 times 2 is 8, 8 plus 1 9, 9 by 4, and this is equivalent to, now we can take square root, after adding 9 by 4 to both sides, I am skipping one step. This is greater than or equal to square root of 9 by 4. If and only if absolute value of x minus 1 by 2 is greater than or equal to 3 by 2. If and only if either x minus 1 by 2 is greater than or equal to 3 by 2 or x minus 1 by 2 is less than or equal to minus 3 by 2. If and only if the first inequality is equivalent to, if you add 1 by 2 to both sides, you will get x is greater than or equal to 1 by 2 plus 3 by 2 is 4 by 2, that means 2. Or here also you add 1 by 2 to both sides. 1 by 2 minus 3 by 2 is minus 2 by 2, that is minus 1. So in this case the solution set is a union of two intervals. One of them is this, x is less than or equal to minus 1, and the other is x is greater than or equal to 2. So this is the solution set. Okay. Now leaving the numerical exercises, we now see some theory and examples. Do not fall into the trap. that absolute value of minus a is equal to a. Some people will be tempted to just get rid of the minus sign and write a simply because absolute value is there without bothering to see what a itself is. So this is wrong, it's not always true. We now have to find when it's true and when it's false. For what real numbers a is this equation true? And for what real numbers is it false? Okay, I think I need ink, it's fading. Okay, as a real number, a is either non-negative or negative. If a is non-negative, then we can actually dispose of one case in the beginning itself. If a is equal to 0, then obviously this equation is true, because the left hand side will be 0 and the right hand side will also be 0. If a is greater than 0, then minus a is less than 0, and hence absolute value of minus a, since minus a itself is less than 0, by definition of absolute value, this will be equal to minus of a, and that is equal to a. If a is less than 0, then minus a is greater than 0, and hence in this case this will be equal to minus a. So we can see thus for a greater than or equal to 0, the equation is true, and for a less than 0, the equation is false. So since it involves a general real number a, the question is theoretical and the answer is also theoretical. It completely determines the values of a for which the given equation is true. In fact, if someone asks you to solve this equation, then this is the solution. The solution is the set of all non-negative real numbers. You can verify by taking a non-negative real number. For 0 we have already seen. If you take say a equal to 1, then absolute value of -1 is 1, which is also the value of a. But if you take in place of a in negative numbers, say -2, then minus of -2 becomes +2, whose absolute value is 2, which is not equal to a because a is -2. So for negative a, it's not true. Okay, then I didn't write exercise here. 44. Solve the equation absolute value of x minus 1 is equal to 1 minus x. So you can see that this equation is just like this one, where in place of a we have 1 minus x. So we can use the previous solution. From the previous exercise and its solution, we get if and only if a has to be greater than or equal to 0, which is equivalent to this. So the solution set, not that although we are given an equation, but still we are getting a solution set. In fact, when we encountered equations also involving absolute value, there we got two solutions. In this case, since x is there inside absolute value as well as outside, so we are getting an interval, in fact a ray. The solution set is the set of all real numbers not exceeding 1, that is less than or equal to 1. So this is the solution set. (45) A proof of the triangle inequality. Give the reasons justifying each of the numbered steps. Each of the number steps in the following proof of the triangle inequality. Okay, so here are the steps. This is equal to a plus b whole square. Recall that the triangle inequality is the last property in the list of rules for inequality that we saw in the beginning itself. A square plus 2ab plus b square. So this is the first step, first number step which we need to justify. This is the second one. This is the third one. And after this, the triangle inequality has been written, which apparently follows from this. But how or why? This is the fourth one. Okay, so let us justify the steps one by one. In the text we have an inequality here. However, if someone wants, they can write equality also. That is also okay. This one. Let's number our justifications also. 1 means justification for the first step. If a plus b is non-negative, then this is equal to, what is the absolute value of a plus b if a plus b is non-negative? The absolute value is a plus b itself. And we have square, so here equality is immediate. If on the other hand a plus b is negative, these are the two possibilities. No? A plus b is either non-negative or negative. Then this square, then absolute value is minus of a plus b, and outside we have square, so this again becomes equal to a plus b whole square. So in any case, if you have square, whether you consider absolute value or don't consider, it does not matter. Then number 2. Okay, in number 2 you can see that you can, if you are just considering this inequality, this is less than or equal to this, then that is equivalent to the inequality which says that AB is less than or equal to absolute value of A times absolute value of B, because from that you can get this one by multiplying both sides by 2 and then adding a square plus b square for both sides, and conversely also. So for the second step, it's enough to justify this. AB is less than or equal to this. Here also we are going to see the cases. If okay, my confusion is, it's not confusion, but I just want to make sure how to proceed. Should I separately show that A is less than or equal to absolute value of A, and hence B is also less than or equal to absolute value of B, and then multiply them? Or okay, let us show it at once. If AB is greater than or equal to 0, then either A and B are both greater than or equal to 0, or A and B are both less than 0. Have I actually covered all the cases? I mean, I am somewhat worried about that 0. Oh, I think it's better to get rid of that 0 case first. If AB is equal to 0, then A is equal to 0 or B is equal to 0 or both. Okay. In any case, if A is 0, then this product is 0, because the left hand factor will be, the left factor will be 0. If B is 0, then also the right factor is 0. So both the product is 0. And if AB is 0, then the left hand side is 0. In any case, we have AB equal to 0. 0 is definitely less than or equal to 0, which is also equal to this. Okay, so assume that AB is not equal to 0. That means neither A nor B is 0. Each one of them is non-zero. They may each one of them is either positive or negative. Now let AB be greater than 0. Then either A is greater than 0 and B is also greater than 0, or both of them are less than 0. That is, they should have the same sign. Either both of them are positive or both of them are negative, so that their product is positive. If A and B are both positive, then AB, if A and B are both positive, then AB is equal to, since A is positive, A is absolute value of A is equal to absolute value of A. Since B is positive, B is also equal to absolute value of A. So in this case, the inequality is true, because the inequality also has an equality. That option is there in this. We are not given strict inequality. So AB can be equal to absolute value of A times absolute value of B. If on the other hand A and B are both negative, then AB can be written as if I write it like that, then it will be more clear. Minus of A times minus of B. It will be clear why I am bringing minus. If A is negative, then minus of A is absolute value of A. So and just like that, minus of B is absolute value of B, and we have one extra minus, and this is equal to this. Okay. Next, assume that AB is less than 0. That's the only possibility that's left. We have considered the case AB equal to 0, then we have considered AB greater than 0, now AB is less than 0. Then A is positive and B is negative, or A is negative and B is positive. That is, they have opposite signs. If A is negative, the first one is this, A is positive and B is negative, then AB is negative, AB is negative and 0 is always less than or equal to this, because each one of these real numbers is a non-negative real number. Absolute value is always non-negative, so that's why each one of them is greater than or equal to 0, so their product is also greater than or equal to 0. So in this case we have strict inequality. AB is strictly less than mod A times mod B, if I call that mod. Similarly, if so in this case there is no need to write these separate conditions. If A is less than 0 and B is greater than 0, then also we will have that same thing. So that's why this inequality is true. You multiply both sides by 2 and then add A square plus B square to both sides. That will give you step 2. Then the third one. The third one is same. Same as the first one. See the justification for step 1. And what about the fourth one? In the fourth one we are given this. And we have been after this the conclusion is that you can get rid of the squares. We can justify this like how we justified taking square root on both sides if the numbers involved are non-negative, but we can take a more algebraic approach. Algebraic approach in the sense that which will involve no graphs. Note that before step 4 we had this. Now this implies zero is less than or equal to square minus this square. And this thing is equal to, if I write like that it may be confusing. Let me just write another implication. 0 is less than or equal to x square minus y square. So this is x plus y times x minus y. Okay. Okay, now what does this tell us? It tells us that the product of two real numbers, one of them is this and the other one is this, is non-negative. So clearly two possibilities are there. Either both of them are non-negative or both of them are negative. This implies this real number and this real number are either both non-negative or both negative. Since this cannot be negative, it can never be negative. We must have the case that both these real numbers are non-negative. By the way, why is this never negative? It's because absolute value of a is non-negative. This one is also non-negative, this one is also non-negative, so their sum is non-negative. It can never be negative. So that's why both of these must be non-negative. In particular, this is non-negative, from where we will get the triangle inequality. We must have this. Which implies this. So that is the justification for the fourth step. Then exercise 46. Prove that absolute value of AB is equal to this times this for any numbers A and B. Here also we can take care of the zero case first. If A or let me write like this, if at least one of A or B is 0, then AB is 0, so its absolute value is 0, and this product is also equal to 0. Okay, so in that case the equality is, the identity is true. Assume both A and B are non-zero. So that means each one of them is either positive or negative. So accordingly there will be 4 cases, and we are going to have a look at four of them. If A and B are both positive, then what about AB? AB is also positive, and that's why its absolute value is just AB. Since A is positive, A equals the absolute value of A. Since B is positive, B equals the absolute value of B. So here also the identity is true. If A is greater than 0, that is A is positive and B is negative, then AB is negative, so absolute value of AB is minus of AB, which can be written as A times minus B. Now A is positive, so A equals this, and B is negative, so minus B equals this. So here also the identity is true. Next, same, if A is negative, and let me just write the rest without saying anything. Lastly, if A and B are both negative, then AB is positive. And so its absolute value is AB. But this is minus A times minus B also. So this is equal to absolute value of A. This is absolute value of B. So in all the possible cases, the identity is true, and hence it is true in general for any A and B. Okay, then some more ink. Three more exercises are left, so let's just complete it. Oh, I need new ink. Okay, let us just stop it here. I have to open the seal of another ink bottle. 3 more exercises are left. We will solve them in the next video on calculus, and along with that we will start a new section, coordinates, lines and increments. Okay, so with this I end this video. If you are new to my channel, please consider subscribing if you find it useful. So with this I sign off. This is me, Lucifer, from a mathematical room. Have a nice night.